So let's find the area using parametric equations. So here we have two parametric equations which represent a parametric curve called an asteroid. And I've drawn the graph as a sketch over here. And you guys, we've got practice with creating parametric graphs, so you should be able to create this graph on your own. I'm just going to go ahead and give it to us. So in this case, we want to find the area. And remember, the area in calculus can be represented by an integral. One thing we notice about this shape is that it is symmetric. I mean, ideally it is symmetric, but I drew it by hand. So it's symmetric. It is this shaded area in the first quadrant times 4. Okay? So it is 4 times the area of quadrant 1. So we could set this up and say, well, this is going to be the area 4 of the integral from 0 to 1, and that is x equals 0 to 1, so that's where my 0 and the 1 came from, of the function y in terms of x integrated with respect to x. Now, looking at this y, what does that y mean? That represents, the y in this formula represents a y equation in terms of x because we want to differentiate with respect to x. Well, creating that parametric curve, that function that would represent it in terms of x and y, is going to be pretty ugly. You'd end up with, sine cubed of inverse cosine cubed of x. We don't want to deal with that because we don't know how to integrate it. So maybe I can write it all in terms of t. So what we're going to note here is that y equals sine cubed of t. And considering that x equals cosine t cubed, well, the derivative of x with respect to t, and I'm taking the derivative of x because I want that dx there. The derivative of x with respect to t would be 3 cosine squared t times the derivative of the inside, and the derivative of cosine is negative sine t. Okay, so really we could say that dx with respect to t is negative 3 sine of t cosine squared of t. And taking that dt and multiplying it over here, we have a direct substitution we can create. So in this case, I have my area equals 4, my integral. I'm going to need to calculate some new bounds for x. My y is sine cubed of t, and my dx is negative 3 sine t cosine squared t dt. So what would my bounds be? My bounds need to be in terms of t, and right now I have a 0 and 1 in terms of x, right? So if I say, well, let's let x equal 0, that would be 0 equals cosine cubed t, or 0 equals cosine of t. I could take the cube root of both sides, and that would let me know, well, I have t equals pi over 2. So pi over 2 would be my lower bound, and a similar argument for 1 equals cosine t, because again I could cube root 1 and still have 1. We would get that t equals 0. So take a moment, pause the video, maybe make sure you know how I've set this up. I now am going to find area with respect to my x and y equations in terms of t. Okay, now one thing I noticed is that my bounds are reversed, and I also have a constant, -3, that I can factor out. So if I pull -3 right here out into the front, that would give me a -12. But flipping my bounds, that would negate that again, so that -12 in front would be +12. So I'm going to rewrite this and say A equals 12, the integral from 0 to pi over 2. And again, that 12 came, the -3 came into the front with the -4, and then I flipped my bounds, which negated my -12. We've got +12. So I've got the integral now of sine to the 4th t times cosine squared t dt. Now, some of our strategies for integration when we're integrating sines and cosines to powers, especially when it's an even power, we're going to use our double angle substitutions. And our double angles, let me just refresh you of what we know. We know that sine squared t is 1/2, 1 minus the cosine of 2t, and cosine squared t is 1/2, 1 plus the cosine of 2t. So I'm going to sub that in, and that gives me my area is 12. I've got the integral from 0 to pi over 2 of, since sine squared is to the 4th, I'm going to have 1/2, 1 minus the cosine of 2t quantity squared, times 1/2, 1 plus the cosine of 2t, and then dt. So squaring this first 1/2, that's 1/4, and I have this other 1/2 that comes out, so that's going to pull out a 1/8. So I've got 12 over 8 as a leading coefficient here, and 12 over 8 reduces to 3 over 2. So I've got 3 over 2, 1 minus the cosine of 2t squared, 1 plus the cosine of 2t dt. So at this point, I'm going to FOIL this out, and I end up with, when I multiply all of what I have in my parentheses over there, 1 minus cosine of 2t times itself, then times 1 plus cosine 2t, I end up with 1 minus cosine of 2t minus cosine squared of 2t plus cosine cubed of 2t. Again, we're still integrating with respect to t. So now I have a polynomial-esque, it looks like a polynomial equation, but we've got trig functions in there for our terms. And my first two terms are pretty easy for me to integrate. The integral of 1 is just going to become t, and the integral of cosine 2t, the integral of cosine is sine 2t, and then we would divide by that coefficient of 2. So we'd have -1/2 sine 2t. The other two are a little more complex because, again, we have powers of sine and cosine that are going to need to be reduced. So I'm going to do each of those as a little intermediate calculation. So I'm going to skip over here. I'll bring it back in. If we were to do the integral from 0 to pi over 2 of cosine squared 2t dt, we would again use a double angle substitution. So this is 0 to pi over 2 of 1/2, 1 plus, and we need to double that angle, 1 plus the cosine of 4t dt. So this piece is pretty easy for us to evaluate. That would be 1/2 the integral from 0 to pi over 2 of 1 plus the cosine of 4t dt, which is 1/2. The integral of 1 is t, and the integral of cosine 4t would be plus the sine of 4t over 4, and we'll evaluate that from pi over 2 to 0. So if I plug in pi over 2 and I plug in 0, I end up with an output value of pi over 4. So going back to my previous slide where we had done our work, we've got that A equals 3/2. The integral of these first two pieces, I've got t minus, that would be sine 2t over 2. We're going to need to evaluate that from pi over 2 to 0. Minus the value I'm going to get here is pi over 4. And then I'll go and I'll do my last piece, cosine cubed 2t, also on a scratch piece of paper. So my integral from 0 to pi over 2 of cosine cubed 2t, and that's with respect to dt. So now this is an odd power of cosine. So in order for us to integrate this, we're going to use double angle and some u substitution here. We'll say let u equal 2t. So that means du is 2 dt. And I'll change my bounds of integration. If I let t be 0, I get that u is, if I let t be 0, I get that u is 0. And if I let t be pi over 2, I get that u is going to be pi. So this integral we're solving can be written as 0 to pi. We've got cosine cube u, and then dt is equal to 1/2 du. So I'm dealing with 1/2 the integral from 0 to pi of cosine cubed u du. In order to solve this, I'm going to write that as cosine squared u times cosine u du. Using some trig substitutions, I can let cosine squared u be 1 minus sine squared u. So this is now 1/2 the integral from 0 to pi of 1 minus sine squared u times cosine u du. And what I'll do here is I'll let v equal sine u, which then gives me that dv is cosine u du. So this integral now turns into 1/2 the integral. Remember, we're going to need to change our bounds. I'll do that in a second. I have 1 minus v squared dv. So if I look at changing my bounds, and I say, well, what happens when I plug u equals 0 and u equals pi? V equals the sine of 0 and v equals the sine of pi. Both of those are 0. So my bounds, 0 minus 0, this is a 0 width interval for my integral. And we know that the value of an integral over a interval, which is only 0 units wide, this is going to be 1/2 times 0, or 0. So skipping back to where we were, for this value we get minus 0. Of course, we're still going to need to spread through that 3/2 distribute. So if I look at evaluating the first part, I have 3/2. I've got pi over 2 minus the sine of 2 pi over 2 over 2, which is the sine of pi, which is 0. So minus 0, plugging in 0 for t, I would get 0 minus the sine of 2 times 0 over 2. Again, that is 0. So this first integral that we were calculating is just pi over 2. I've got pi over 2 minus pi over 4. And then again, I don't need to write minus 0. Pi over 2 minus pi over 4 is positive pi over 4. So I end up with 3 pi over 8. That is the value for the area of the space enclosed by this asteroid. So all of this region that I've shaded in here, this curvy diamond, the area of that shaded region is 3 pi over 8. And of course, that integration got a little complex when we were down on this step. I had to do some scratch work. And there are other ways for you to do trig integrals that we've seen through our practice in class. Okay, so the two ways that I chose weren't the only way. It was just kind of what worked out easier for me in my mind when I was figuring out the problem. And so that is the area of a space enclosed by parametric curves.